In today's video, we are going to discuss the hardware components required for an in-situ leaf area index monitoring system using IoT technology. Leaf area index, it is an important parameter in agriculture that helps measure the plant growth, crop health and vegetation density. To collect this information directly from the field in real time, we need several smart hardware components working together. So let's look at the major hardware required for this system. Now here in this image you can see the architecture of an IoT based leaf area index assessment system used in smart agriculture, and the system combines wireless sensor networks, edge computing, cloud computing and IoT communication technologies to monitor the crop growth and environmental conditions in the real time. Now at the deployment field you can see there are many TelosB sensor modes which are installed among the crops. These modes are commercial off-the-shelf and devices equipped with three sensors, that is the temperature sensor, humidity sensor and the light sensors. The temperature sensor, it will measure the surrounding temperature, while the humidity sensor monitors the moisture level in the environment, and the light sensor is used to measure the sunlight density. To accurately determine the PAR, that is the photosynthetically active radiation, an optical filter and a diffuser. Here you can see optical filter and a diffuser which are attached to the light sensor, and the PAR represents a portion of the light, that is the sunlight, used by the plants for photosynthesis, and it is an important parameter for estimating the leaf area index. The system is followed by it follows a cluster based architecture where you have 4 TelosB sensor, that is the ground sensor modes, communicate wirelessly with a Raspberry Pi which acts as the cluster head. Here you can see it acts as the cluster head. The Raspberry Pi is a compact single board computer capable of collecting, processing and managing the data from multiple sensor nodes. Now here it forms a star topology where all the sensor modes send their readings directly to the cluster head. After collecting the data from the sensors, the Raspberry Pi performs the preliminary processing and it transmits the information to a gateway through the wireless communication. Now the gateway, it acts as a bridge between the local sensors and the internet, and it forwards the collected data to the centralized cloud or the server infrastructure. Now the cloud or the server infrastructure, it is responsible for data storage, processing, analytics and the visualization, and advanced algorithms will analyze the sensor readings and estimate the LAI of the crop canopy. Now the processed information is then presented through the through user applications here. Okay, user applications such as you have like a web dashboards and the mobile phones. Now, one challenge in the agricultural environments is the signal attenuation, which is caused by humidity and the wet plants. So, wet plants or wet plant surfaces, which can reduce the communication reliability. Now, to overcome this issue, the system employs a forward error coding, that is the FEC technique, which adds redundant information to the transmitted data, enabling the receiver to detect and correct errors without retransmission, thereby improving the communication reliability. Finally, the farmers and the researchers can access the analyzed information through the computers or the smartphones. And the system supports the real-time monitoring, alerts, decision support and the precision farming, helping the users to improve the crop management, optimize resource usage and enhance the agricultural productivity through the IoT enabled smart farming technologies. Now here in this image you can see the real deployment of the IoT based leaf area index assessment system, which is used in agricultural fields. The system is designed to provide the reliable data collection and transmission under challenging environmental conditions such as humidity, then rain, wildlife interference and plant growth. Now to ensure dependable communication, the system uses a redundant approach that combines both wired and wireless connectivity. Now here in the upper part you can see you have the first deployment generation, which is of wired connectivity. Now in this setup, the sensor modes, these are deployed in the crop field are powered through a USB power supply, and the USB connection serves two important purposes, that is the supplying power to the sensor nodes and enabling the configuration, then maintenance and data access when required. Now a Raspberry Pi here, it acts as a cluster head. Okay, this will act as a cluster head and gateway collecting sensor readings from the field. So to conserve energy, a mechanical timer is installed which automatically switch off the sensors during the night and when the measurements are not needed, and the collected data is then transmitted to the cloud server for storage and analysis. Although this wired system provides a stable communication, it requires physical cables which may be difficult to manage in large agricultural fields. So the lower part here, this part, that is here it shows the second deployment generation, that is the wireless connectivity. In this improved design, ground sensor modes, these are equipped with the external antennas here. You can see the antennas here. These are equipped with the external antennas, and these increase the communication range and the signal reliability. So the sensor nodes form a wireless cluster and communicate directly with the Raspberry Pi cluster head using a star topology. Now this will eliminate the need for extensive wiring, making deployment easier and more flexible. A significant enhancement in this second deployment generation is the use of Raspberry Pi with long-term evolution. Okay, that is the LTE capability, which is a cellular network, and the Raspberry Pi acts both the cluster head and the gateway and transmit data directly to the cloud through the cellular network. Now this will allow the real-time communication even in the remote agricultural locations where traditional internet infrastructure may not be available. So the cloud server, the cloud or the server infrastructure stores the sensor data, performs the processing and analytics, and estimates the leaf area index and will generate visual reports. Now farmers and researchers can access this information through the computers and mobile devices for real-time monitoring, alerts and the decision supports. So overall, the second generation wireless architecture offers improved scalability and easier installation, greater mobility and more reliable communication, making it a practical solution for smart farming and the precision agriculture applications. So here at the bottom you can see different components which are being used. So you have a USB which is used for power configuration and data access. Then you have mechanical timer, you have external antennas, and then Raspberry Pi with LTE. Okay, so this is about the hardware components which are used in the in-situ assessment of LAI using IoT based agricultural system. Thank you.